All right, guys. So we're going to take a look at thermochemistry. It's broken into 3 parts. And so we're probably going to get through this in a week because it's relatively quick. The last section should be the longest, but all right. U.S. energy consumption by source. This is all thermochemistry, biomass, hydropower, wind. All of this comes together and has something to do with some amount of physics, but a lot of chemistry, burning things, combustion reactions, or or solar. All these things, nuclear. All these things are in fact chemistry related or thermochemistry. Anytime you have energy involved with chemistry. So excuse me. So just take a look at these. We'll talk about these briefly. Are you shocked at all by these numbers, or I guess depressed maybe a little bit? But we'll talk about it on Monday, or at least we'll talk about it in first class this week. Okay, so we're going to talk about the energy basics. So in order to talk about the energy basics, we have to know what energy actually is. So looking at energy, what is the definition of energy? So energy is the capacity to supply heat or to do work. By the way, I got myself a new pencil, so my writing looks better. But supply heat or do work. So 2 of those things. So that means work and heat are related to one another. So we need to define both of those. So let's start with work. Work is something we don't see a whole lot in chemistry because what it has to do with is moving matter. So moving matter is when we perform work on something. So moving matter against an opposing force. So as the example I typically use is, here's my glass or drink. By lifting it, I'm moving the matter. I'm moving the glass along with the liquid in it, but I'm moving it against the opposing force being gravity, right? So so that's what we're looking at for moving matter. Anytime we see moving matter, in terms of in the chemistry lab, we don't really see a whole lot of it. You see conversations about when we look at pressure and volume changes. That is really when we're going to see work. So pressure and volume is changes is the only time you're ever going to see work being done on the system or the surroundings, and we'll talk about that. So the equation for work is force times distance, force times the distance that it traveled, and that's going to come into play a little bit later when we talk about the units. All right, next let's take a look at heat. So heat is more important. Heat is denoted by Q. We're going to use Q a lot more often than I'm going to say heat. So know that heat is equal to Q, is the transfer of energy due to a difference in temperature. So that's it's a transfer of heat. In fact, both of these are a transfer of energy on matter. Work, you're moving matter with a force that's opposing it. You're moving matter, you're transferring energy. So both of these are transfer processes. So again, let's take a look at moving matter. For work, we are transferring of energy by any process other than heat. By the way, these 2 things are going to come together to give us the first law of thermodynamics. And that's kind of what the basis of all this thermochemistry is on, energy transfers. So transferring energy. So work, again, moving matter, but it is a transfer of energy by any process other than heat. Okay, so transferring of energy by any process other than heat. In terms of heat transfers, we see heat transfers in a couple of different ways. So heat transfers transferred by, heat can be transferred by conduction, by radiation, and by convection. Okay, so the example for conduction is if you put a spoon into, let's say, put a spoon into hot soup, all of a sudden the spoon heats up and the soup cools down a little bit. So that's the example of conduction. Okay, radiation, fire, right? That's emitting infrared radiation. That's heating up molecules, so it's a transfer of energy. And then convection is a little bit different. Convection is actually the differences in density. Densities of a fluid caused by temperature differences, temperature deltas or delta T's, okay? So again, radiation is something like a fire or electromagnetic radiation. Conduction is transferred direct matter, direct contact with one another, so like a hot spoon or cold spoon, I guess I should say, in soup. That's a direct transfer. So work and heat are two ways in which energy is transferred. One more time, energy is transferred. When I say heat or work, I'm always talking about the transfer of energy. If there's no transfer of energy, there's no heat or work done. Again, these are both processes. They are both a process. Okay, yeah, processes. So you can't have one without the other, as in they have to be a process. We're talking about the transfer of heat, not something specific. I can't talk about the energy of, we can talk about the energy exchange, but that's it. It has to be a transfer of energy. All right, so the ones that we know well and the ones that we can actually kind of look at are kinetic energy and potential energy. So you guys know the definitions for these probably, but here we go. Let's do it again. Kinetic energy is energy associated with movement or associated with the motion of an object. And that doesn't really change. It's the same thing in chemistry. So mass times the velocity squared. Again, because it's squared, the inverse square, the velocity is much more important than the mass. And of course, potential energy is the stored energy that is stored by an object by virtue of, and this is always fun, it's by virtue of its location. By virtue of its location in a force field. Okay, well, what the hell is a force field? And a force field comes in many different forms. Gravitational or electrical, I should say, or magnetic. So gravitational is easy. I have an apple in the tree, right? If I drop an apple, it's in these forces. The forces are pulling down on that apple, and it has potential energy until it starts moving. Electrical energy, so potential differences in positive and negative. Magnetic differences, are you attracted? Kind of actually very similar to electrical. So again, positive or negative, attracted towards north or south, those types of things. And the equation is mgh, mass times gravity. In this case, that's the field that we're talking about. And then height being how far away it is. And we could look at this, these two are kind of equal and opposite in a lot of ways. So there we go. That's my graph of energy, and that's my zero coordinate and we're talking about progress over time. So if we're to look in, hopefully I can get this right. So the top little bit here, there we go. That top point there is the total energy. And we have the kinetic energy increasing to a maximum and then decreases. So that's the kinetic energy. When we're still, we don't have any energy whatsoever, right? So when the potential is at its maximum, there's no motion whatsoever. So that's the potential. So if you imagine where we are, so right up here, we have a maximum potential energy because there's no motion whatsoever. And as we lose potential energy, that means that we're increasing kinetic until we reach a maximum of both, a maximum and minimum. And then once it hits the ground, we again have a maximum potential again, or I guess we shouldn't say ground because it could be in a different space, especially because it would have no potential energy if it actually hit the ground. But anyway, they're equal and opposite in a lot of ways. Again, the direction of lower potential energy is the direction of the bodies would move on their own. So we do see a lot of those types of transitions where you see we're always going to try to go to a lower energy state. That's kind of the thing that chemistry likes to do. So next we're going to talk about thermal energy, temperature, and heat, and how they all relate together. Again, we need a handful of definitions for these things. So thermal energy is the kinetic energy associated with the random motion of atoms and molecules. Unless we're at absolute zero, and we'll talk about absolute zero eventually, unless we're at absolute zero, atoms are vibrating, they're rotating, they're doing all sorts of different movement. In fact, there's a bunch of different rotations. And so a molecule can vibrate, it can rotate, and it can translate. So vibration is shaking, rotation is spinning or turning, translate is actually moving left to right, so translate. So those are the types of thermal energy that we see. So here we have hot water and cold water. Hot water, we see those a lot of force lines around it, so they're moving a lot, they're shaking a lot. Cold water is not so much. Temperature is just simply a quantitative measure of hot or cold. I'm putting those in parentheses, or yeah, I'm putting those in quotes because hot or cold can be defined in very different ways. So it's a quantitative measure because we are putting numbers to it. 25 Kelvin or 0 Kelvin. Those, I'm sorry, 25 Celsius or 25 Kelvin. Both of those are measures of temperature, and they're quantitative because there's a number associated with it. But ultimately, what happens is the higher average kinetic energy equals hot, right? So the more energy we have, the more motion we have, the hotter it actually is. So that is thermal energy and temperature connected together. So now we have to relate these things to heat. Remember, heat has nothing to do, hot water and cold water has nothing to do with, so how much heat is present in hot and cold water? The answer is nothing, because heat is, in that reference right there, how I said it, it's a measure of temperature, but that's not true. Remember, heat is a transfer of energy. So here I have my hot and my cold, like I did on the previous. I put them together. So I have this little insulator in between them, and then I connect them together. So they've made contact with one another. And that little arrow there represents the transfer of energy. And this little pictogram does a good job of it. The red to blue, I guess that's the colors we typically use. Notice the red is becoming less red and more blue. The red is becoming less blue and more red, so it's turning to purplish, and we get this transfer of energy. And eventually what we reach is a thermal equilibrium where the temperatures are equal. So the temperature of equal temp when we get to that. So there's going to transfer energy. The hot will be cooler, but not as cold as it was. The low temperature will be hotter, but not as hot as it was. They're going to equilibrate left. We're always going to transfer. And that's the important part out of all of this. We always transfer from hot to cold, right? So high temperature transfers to low temperature, and really a little bit of the other way as well. Not really the other way, but hot temperature moves to low temperature. Low temperature is going to increase because of the presence of the hot temperature. So when you open the window and you get a bunch of heat leaving, and your mom yells at you, or father, or whoever yells at you and says, you know, hey, close the window, you're letting the cold air in. Well, no, technically you're letting the hot air out, right? Because the hot always has to transfer from hot to cold. Yes, again, that's a convection thing. But yeah, technically you're letting the hot air out. That's how thermodynamics works, right? All right, so matter undergoing chemical reactions. So all of these things involve changes in temperature. All of these changes in temperature, we kind of avoided it from thus far, but chemical reactions and physical changes, those two things are going to release or absorb energy. So we call those two things, and again, release or absorb heat, energy, and there's a reason that I connected those two things together, because typically work is not involved. So we can typically call energy and heat the same exact thing. But anyway, in any event, so the release or absorption of heat. So we have two terms, endothermic and exothermic. And again, I told you how to memorize this or to know this. Remember, going from solid to liquid to gas, those are endothermic processes. We need to break bonds, or I should say break interactions, in order to do endothermic. And we need to form bonds in order to have something that is exothermic. And we're going the other way. Okay, so forming bonds is exothermic. We get energy back. So those two terms, getting energy back, we don't really typically say it that way. Endothermic, really, the term that I'm looking at, or we should be looking at, is the absorption of heat. You might say, well, the absorption by what? And we're going to talk about this in just a little bit, but by the system from the surroundings. So the surroundings, so the system is the chemical reaction that's happening. The surroundings are everything else outside of it. And we're going to talk more specifically about that. But the absorption of heat is the reaction is absorbing, drawing in heat from the outside, right? Because the outside is warmer and the reaction itself in an endothermic situation is colder. So the heat transfers into, it gets absorbed by the reaction that's happening. On the other hand, we have the release of heat, which is an exothermic, and that seems a little bit more straightforward. Release of heat by the system into the surroundings. So this is a situation where the system is releasing energy, and that energy is going into the surrounding. So we can look at that in two different ways. If we see like a combustion reaction, here we have an acetylene torch. This is exothermic. It's releasing energy because the system, the reaction is just breaking a bunch of bonds. I'm sorry, it's forming a bunch of bonds, forming more bonds than it's breaking. We'll talk about that when we talk about enthalpy. It's just going to release a ton of energy, and that's that. On the other hand, this chemical reaction in the cold pack does quite the opposite, and does a really good job of it. It's actually, the chemical reaction is going to form more bonds than it breaks, and therefore it's going to break more bonds than it forms, and it's going to start pulling in. If you're asking yourself at this point, how can you have a decrease in energy like that? Well, we're going to talk about the idea of enthalpy versus entropy. And it turns out you can go in the other direction if you do in fact have an increase in randomness of the universe. So it's a pretty neat topic to talk about. So let's talk about the units of energy. So we're going to talk about 2 units of energy. First of all, calories. And this is the one that we probably know best. Calorie is the energy required to raise 1 gram of water by 1 degree Celsius. One degree C, I guess I should say, or Kelvin, because either one would work, right? At the same scale. So the amount of energy required to raise 1 gram of water by 1 degree Celsius. That is technically what a calorie is. Okay. So, yeah, good. And versus a joule. A joule is the SI unit. So the joule is the SI unit. It is the amount of energy used when a force of 1 Newton, of 1 Newton moves an object 1 meter. So both of these are related to transferring of energy. Calorie, notice that definition is talking about the transfer of heat energy, where a joule is actually talking about moving an object. So that's work energy. So we have 2 versions of it. But good news is we actually have something that makes them equal. So 1 calorie, gotta be very specific here, 1 calorie is equal to 4.184 joules. And calories, so 1 cal, lowercase c, 1 or 4.184 capital J joules. Okay. So the reason that I just said that, by the way, I mentioned it. Weirdly enough, this is kind of how this works. And I'm sorry we're in America, but this is kind of where we're at. If you look at the back of any food packaging, in fact, if you can look at it right now, you're going to see 1 capital C calorie. Well, it turns out 1 capital C calorie, for some reason, because we don't use the metric system, is actually equivalent to 1 kilocalorie, which is equal to 1,000 lowercase calories, or regular calories. And let's complete the idea. 1 kilojoule is equal to 1,000 joules of energy. Again, a capital C calorie on the back of food packaging actually means kilocalories. If you go anywhere else, literally anywhere else in any other country, they're going to use kilocalories on the back of food packaging. So yeah, America, here we are. So measuring energy and heat transfer. So all of this conceptual stuff doesn't really do us any good unless we can kind of put it into action. So heat capacity. There's 2 things: heat capacity and specific heat capacity. First of all, heat capacity is a little bit different. Heat capacity, C, capital C, is the quantity of energy required to increase the temperature of a sample by 1 degree. This part right here. So we have 2 different samples. We have a small and a large cast iron pan. But both of those count as the sample when we're talking about it. So the sample in this case can be different. There's no standardization here. So in this case, the specific heat, or the heat capacity, not specific heat capacity, is determined by the amount of the substance. So if this is iron, it determines the amount of heat capacity is basically going to be based on the size of these things. This is known as an extensive property. We're going to run into this word again. Extensive property just means that the amount, the amount matters, right? An intensive property is going to be the amount does not matter. Volume is extensive. Density is intensive, because density is basically saying, oh, doesn't matter what it is, water always has the same density. but 1 liter of water versus 10 liters of water, those are different values. So weird, but this is how it works. So specific heat, or I'm sorry, heat capacity is equal to heat over the change in temperature, so delta T. If I were to rearrange this, because typically we solve for heat, Q is equal to, is equal to C times delta T. Again, that change in temperature of the heat capacity, we typically don't use this as much as we use something like specific heat capacity. Specific heat capacity is the quantity of heat required to raise the temperature of 1 gram of that specific substance 1 degree Celsius. So you can see water has 4.18. If we focus in here on water, water has 4.16 joules per gram times degree C. This is also 1.000 calories per gram times degree C, right? So it's what it costs to raise the temperature of 1 gram of a substance 1 degree Celsius. So 1 calorie, 1 degree, 1 gram. So anyway, so let's take a look at the heat, take a look at the equation. So specific heat, lowercase c, you might see S, you might see CS. I have CS here, and you're going to see why in just a moment. This is the specific heat of some substance. It's got to be defined. And this is important to mention, but phase matters. There's no pun intended here. So what we notice is water has a specific heat capacity of 4.184. Ice, same substance, different phase. So this is liquid, this is solid. They have different heat capacities. In fact, steam has a slightly different one as well. It's a gas. So temperature and actually phase matters. Aluminum solid, iron solid, glass solid, copper solid, mercury liquid, gold solid, ethanol liquid, air, I guess technically gas, potassium solid, seawater liquid, nitrogen gas, helium gas. And what we're noticing is specific heat capacities are kind of all over the place. But the metals, right? All of the metals tend to do a pretty good job of, or have pretty low specific heat capacities. So they do a good job of transferring, or taking on a change in temperature. Okay, so we're going to look at a bunch of examples of this. All right, so specific heat capacity of the substance, mass of the substance. And delta T of the substance. So all of these things are related to the same substance when we're looking for the Q value, which remember Q is the heat transferred, is the amount of energy transferred. And of course, because this all depends on the type of substance, this is an intensive property. Okay, good. So pretty straightforward. The last little bit, molar heat capacity, the quantity of heat required to change the temperature of 1 mole of substance, 1 degree Celsius. You don't see this as all that often, but I wanted to make sure that you were aware of it. Q is equal to Cm times moles of that substance times delta T. So again, the only difference is we're including molar heat capacity of here instead, right? And in terms of units, we probably should take a look at units quickly. So let me go back up. Q is equal to C times M times delta T. So if we take a look at these units here, specific heat capacity is joules per gram times degree C times grams times delta T, but it's just going to be 1 temperature. So degree C could be Kelvin as well. Degree C cancels, grams cancels, and we're left with Q is equal to joules. Okay? And so the same thing down below, we're going to have molar heat capacity. It's going to be very different, but ultimately the unit should always, unit for work and heat should always be joules or calories. Okay, good. Okay, so that's it. So you can do the problems now. We're going to take a look at these in class, but yeah, So take a look at these, try to get through them, see how you can do.